Okay, so thank you very much for the invitation in this fantastic place, IMPA in Rio, and for this special occasion for Frank's birthday. So Brazilian colleagues told us that they really enjoyed the nice experience in Rennes, but I must say that even for a French person, I've always felt also a special atmosphere in Rennes that you don't feel in many places. And first as a student and then as a colleague, I've really enjoyed it. And of course, Frank is one of the person who makes this atmosphere really nice for us. So today I will speak on a joint work with Stefan Québecus and Frédéric Touzé, another colleague from Rennes. So the motivation is to present a generalization of Bloch-Ochiai theorem. So first of all, I should recall the classical statement of Bloch-Ochiai. So the classical Bloch-Ochiai theorem. So Bloch refers to André Bloch, a French mathematician from the beginning of 20th century, who in fact essentially has created the field of what is now called Kobayashi hyperbolicity, but much before Kobayashi, of course. So he had this intuition of the following statement, which is at that time a bit amazing. So in fact, so of course there are the articles of Bloch, which are today a bit difficult to read, certainly some gaps, but many fantastic ideas. Then there was, like 50 years after, work of Ochiai, and the missing part was given by Kawamata, because you will see that there is some result needed about geometry of subvarieties in abelian varieties. And this final step was done in the 80s. So the setting is, let's say, X complex projective. Manifold. And we will assume that we have many differential forms on it. So the so-called irregularity of X, which is just the dimension of space of global one forms, holomorphic one forms. And we suppose that it's big in the sense that it's strictly larger than the dimension of X. Then, we are interested in the geometry of so-called entire curves. So this is by nature analytic object. This is holomorphic map from C to X. And what you prove is that such an object cannot be Zariski dense in X. So in other words, if you look at the Zariski closure of the image of F, it is not the whole variety. It has to be in a proper fixed algebraic subset. But be careful that this algebraic subset depends on the curve, because you can certainly have such X which are covered by entire curve. Just take, for example, Sure, yeah. The convention is to call entire curve a non-constant holomorphic map. You're right. Important. So just take, for example, a product. It certainly satisfies the hypothesis of Bloch-Ochiai theorem, but you see that if you take the union of all these P1, it covers your manifold. So this algebraic subset really depends on the curve. So as I said, at the time of Bloch, it was a bit amazing to think something like that, but now it really fits very well in the main conjectures of the field which appear much after Bloch. And certainly this is, so I will explain you how to relate this to the so-called Green-Griffiths-Lang conjecture. Which tells you a related result, and a kind of same spirit is that the distribution of entire curves in algebraic manifolds are really controlled by differential forms. So here you see that the key object is one form, but in fact we will see in the talk that you should in fact consider all differential forms, meaning all section of any exterior power of omega 1. So in this conjecture, you look at the extreme case, the highest weight. So you look at section of the so-called canonical bundle, the determinant of the cotangent bundle. So again, let's say X complex projective. And the hypothesis here is that X general type. So this means exactly what I've just told you, is that if you look now at the canonical bundle, you assume that it has, or its power, have the maximal number of sections. So if you look at the growth of this space as a function of m, it will grow like m to the dimension of x. So this is another positivity property of sheaves of differential forms. You see? Different, but kind of same philosophy behind. And here, we should have, in fact, an if and only if, and this time the algebraic subset should be fixed. So if and only if there is a fixed algebraic subset which contains all entire curve. So in some sense, this is stronger than here. Here, it cannot a priori be covered by entire curve, right? So of course, non-constant, again. It should lie in this Z. Okay, so now I want to make a bridge between these two conjectures. So this conjecture was made in the 80s. So what is the relation? So of course, the key character here in between the two conjectures. So here, we look at a differential one form. So the key object will be the Albanese. Right. So look at the Albanese map. And here, the hypothesis can be translated in saying that the Albanese has dimensions strictly larger than the dimension of X, right? So if you look at the image of X, this is certainly a proper subvariety of the Albanese. Right? And now you use the geometry of subvarieties of abelian varieties. And we have a very nice understanding of them due to Ueno. So there is like a dichotomy, right? So either Y is a subtorus or translate of subtorus, but here it's not possible by definition of the Albanese, right? So is a translate of subtorus, but here impossible by definition of the Albanese. So we are in the second possibility, which tells the following, that we have the so-called Ueno reduction map. So there is a subtorus So essentially here you look at the subtorus which stabilizes Y, and you quotient. And a reduction map so you end up in the quotient. And this, what Ueno proves is that this W is of general type. And there has to be a strict positive dimension and W general type. So now it's kind of easy to relate the two conjectures. So this theorem really is conjecturally implied by this theorem, because now you look at the composition map. So we are interested in entire curve here. So you first go to the Albanese, and then you go to the... And of course, if you add a Zariski dense curve in X, since all these maps are dominant, you would end with a dominant map with the Zariski dense entire curve in W, which would contradict Green-Griffiths-Lang conjectures. Right? So this statement somehow should be now seen in this modern point of view as really a very nice illustration, evidence for Green-Griffiths-Lang, which this one is completely open, even for surfaces in general. So, yeah, so now I want to make a bridge to another level of conjectures, which was more recently made by Frédéric Campana, which gives now kind of a very nice global picture for any projective varieties. So here you see I've restricted to general type. So Campana will give a setting where you should be able to understand things for all projective varieties. So I've always made the remark that this hypothesis certainly doesn't imply that X is of general type. Right? You still have the example on the board. But what it implies, as we've seen, is that there is a dominant map to something of general type. So now you see that really what you can look at is rather, if you consider the pullback by H of the canonical bundle of W. So these give you a line bundle which sits into the exterior power of omega x power equal to dimension of W. And Kodaira dimension of L is equal to dimension of W, right? Because W is general type. So you have achieved to find a subbundle in this sheaf of exterior power, which in fact attains the maximal possibility. So this is a theorem of Bogomolov, which tells you that if you have such an object here, its Kodaira dimension cannot be strictly larger than the dimension of W. And this is what we call today a Bogomolov sheaf. This is what has inspired Campana. So definition. Yes? What I said here is that I found a line bundle which sits into this. Bogomolov tells you that if you have in general a rank 1 here inside here, then its Kodaira dimension is less than P. A priori, if you have a line bundle on a variety, its Kodaira dimension could go to dimension of X. But if it lies inside here, it cannot exceed this. And here, we have attained the maximal possible Kodaira dimension, right? So this is what has inspired Campana, saying that X is special if and only if it has no such subsheaf. Strictly less. Okay? So this should really be thought of the most far away from being of general type. Of course, it is not of general type, but it cannot dominate something of general type like this, and even in a stronger sense, using pairs. And now, one of the most general conjecture you could formulate in this kind of question is the following. So X is special if and only if there is a Zariski dense intercurve. So it should really be the geometric characterization of varieties admitting Zariski dense intercurve. Okay. So now I've explained you the setting, so now I want to go to trying to extend this theorem to give more evidence, in some sense, to Green-Griffiths-Lang. So of course, there are some, yes? Yeah.
Does this imply something about the Kodaira dimension of X or not?
Of X. No. So I've told you that here.
Because the Kodaira dimension of X should be related to omega to the power dimension of X.
Yeah.
So this
but you
does not imply anything about the Kodaira dimension of X.
expect some extreme case,
Yes.
like cannot be minus infinity or some. Yeah, but it's not. You don't have. You cannot compute the Kodaira dimension directly from this. No. So. Okay, so one of the first thing you could do, so I want to say some in the spirit of Bloch-Ochiai, working with one forms, because it's convenient, right? It has many good properties. So one thing you could do is somehow generalize the notion of irregularities. So you could start with a variety which has not enough one forms, so you cannot apply Bloch-Ochiai, and you say, okay, let's look at cover. So this is the most natural thing to do. So this is what people call augmented irregularity. So you look at the sum of all irregularities of finite étale cover. Okay? And you could be lucky and have attained, even though if it was not the case for X, maybe this one could achieve this, right? And then you can apply Bloch-Ochiai. That works. So this certainly gives, even though the forms live upstairs, that there is no, in the original manifold, because it's very easy. So you have finite étale. Since it's étale, you can certainly lift your curve, right? And so here, if you had something dense here, it would give something dense here. This would contradict Bloch-Ochiai, right? So this is very easy application. So one of our motivation is, I will show you that our generalization will apply to some simply connected varieties. But of course, if you start with something simply connected, you will, of course, never achieve this. You're losing at étale cover. You have no étale covers. So this certainly gives that you can do nothing with that. But we will be able to say something even in some cases where it's simply connected. And somehow, so this is the first obvious. And some of the detour we made, yes?
It's 0 or?
Yeah, 0. No, I mean here it's simply connected, so Q tilde of x is Q of x. And simply connected, you have no forms, right? So it's 0. Yeah, so the detour I will make is that we initially went to working with pairs, as is now kind of usual in algebraic geometry. So first, people looked at the logarithmic case, so where D will be reduced SNC. And here, you have a very natural notion of irregularities to look at logarithmic differentials. And indeed, you have really the analog. This is a theorem of Noguchi-Winkelmann. So of course, this is technically more delicate, but essentially the proof I've explained you of the classical one is the same. You replace the Albanese with the quasi-Albanese. And you have the same statement. So suppose you have such an estimate, then you can control curve in the complement of D. Zariskidis, right? And some other starting point of the project with Stefan was, well, what about more general pairs? where here you could allow a rational coefficient on D. Even the statement is not clear. How do you state a meaningful statement in this setting? And strangely, in the end, it will apply, interestingly, even when there is no boundary. So the question is, what if D is not reduced? So what time is it? Okay. So I will enter just for a few minutes the world of what we call with Stefan C pairs, but Campana called that orbifold pairs. So let's take D Q divisor with a standard coefficient like that, rational, and the mi are non-zero integer or maybe infinite. And as I say, so first of all, how do you define for such an object a notion of irregularity? It's not clear. What does it mean to be a differential forms on such a pair? So we would like to define sheaves of differentials looking like logarithmic ones, but with fractional pole order. Right? Of course, this has no meaning on X. But you can at least locally give a meaning of that on a cover of X, but not étale, but a ramified cover. So to do that, what you do is you consider adapted cover. So you leave the word of étale. You have to ramify, and ramify over this D. So this is very classical and was already used to prove a vanishing theorem. So we have a whole technology to do that in algebraic geometry, to construct cover which ramifies at least where you want. You may have to include extra ramification, but at least it will, by pullback, make this Q divisor with integral coefficient. So such that gamma star D is integral. And now you can cook up a sheaf. So you could do that by hand with coordinates, but there is a very elegant and direct way to do that, is to pull back the residue exact sequence. So you will define your sheaf. So this is the sheaf you want to define, and you define it as a kernel of the pullback of the residue exact sequence. So this now has a meaning. So be careful that now everything is defined upstairs. You have left X, now you work on X hat on the cover. So this may be a bit strange, but this makes exactly the job you want. If you look at in local coordinates, what are the generators here? It's exactly the formal pullback of this one. So now this is the sheaf you have defined. And now you have a well notion of irregularity. Just look at global section here. So you must, of course, keep in mind that it depends on gamma. So this irregularity now depends on gamma. If you want something that does not depend on gamma, then you mimic the other definition. you look at all covers. And you define Q plus, which is just the sup over all adapted cover of this. Okay? And now you could formulate, if you are interested, you could formulate a Bloch-Ochiai questions. So this is maybe, yes? Yeah, so you just, here is just the support. The support. So it's the roundup of coefficient, so you just put 1 here. Okay, so this is the support of D. So this is just the usual logarithmic shift that you are used to work with. And downstairs you have the residue sequence. You pull it back. And this perfectly makes sense because this is integral now. Okay? And this is defined as the sheaf of this map here. And just to keep in mind, if what I was saying, if you want to be like a bit concrete, really locally, you take local coordinates, it will just mean that you can, if you look at the formal pullback with gamma, this will be the generator of this sheaf.
You divide by mi minus 1, right?
No, by mi.
But gamma star of di is mi di.
Yeah.
And then it cannot be reduced.
Why? What?
So this is n1 minus 1 times mi divided by ni squared.
No, okay, so this, let's say you have an adapted cover, so this gamma, you pull back di.
Oh, okay, you don't put the coefficient.
Okay? Yeah, no, I think this is the correct definition. Okay, so now you could formulate a Bloch-Ochiai statement. So Bloch-Ochiai for pairs, at least, and ask what that the usual so everything now has a meaning except maybe this. What is an entire curve in a pairs? So in a log pair, I've told you, you look at map in the complement. So I will not enter detail, but if you take a smooth pairs, essentially it will mean that you can study curves. So you have your x, and you have this di. You look at curves such that when they touch di, they will have to be tangent to this di to the order at least mi. So the philosophy is that such an hypothesis should be enabled to control such entire curve. So now they can touch di, but they have some prescribed tangency property. Okay, but now, so strangely, at some point, so we developed this, and we said with Stefan, well, what now if we take d0 in this? And funnily, it's still interesting. So if you take d equal to 0, what is this sheaf? This sheaf is just the pullback by gamma of omega 1. Okay? And now, you see, you have somehow enlarged the world of possibility. Here, you were restricting to étale covers. Now you want to look at irregularity in this more general sense. That you look but now you allow, you see, you have no D, so you have no constraint on gamma. Can ramify where you want. You have no D. So you have much more, in some sense, object to work with. And interestingly, so what makes this feel you are not working with some empty set with no interest is that there is example which you can find in papers of old papers, in fact, of Campana, in some construction, you can look at his example, and in fact, even in dimension 2, so there exists simply connected surface so therefore, as I told you, the classical irregularity is certainly 0, but with Q plus, in fact, not only big, it goes to infinity. Right? So you see that the subject, in principle, should be able to deal with these examples. And in fact, these examples are really related to Campana theory of pairs. So they are just vibration over P1. So it looks a bit strange. So how do you create forms on covers like this? But the important point is that it has singular fibers. So that you should rather see the base of the vibration as a pair, and this pair is in fact of general type. And it's very easy to see that this hypothesis implies this. Because here, if you have hyperbolic pair, you can uniformize it by hyperbolic curve. And then you can take cover with as many forms as you want. And you pull them back to the cover induced on X. Okay? So,
But you no longer can lift for free the entire curve.
Exactly. That's the main difficulty we have to deal with. So, this is not at all of course, the end. You have not proved essentially nothing, but just try to convince you that the setting is interesting. And it, of course, poses many questions, in fact. And at the beginning, it was a bit strange to see that it seems that this kind of irregularity has not been studied. At least we have not found many papers related to this. And so by lack of time, I will not read the complete Bloch-Ochiai, but already the first question is not trivial at all, is the following. So it took us some time, in fact, to prove it. So the first question is, if you want so you remember what I've explained to you is that the philosophy is that a variety with big irregularity is not special. It maps to something of general type. So now I want to prove the same. Is it true that if you have such a statement here, then X is indeed not special? You should at least first prove this to prove some Bloch-Ochiai statement, right? So, and then you could ask, indeed, the Bloch-Ochiai one is that there is no Zariski-X. So, the first naive strategy we tried to do, well, all proofs of Bloch-Ochiai that I know relies on the Albanese. They all pass through the geometry of subvarieties in abelian varieties. So we said, okay, let's try to do that, like in Noguchi-Winkelmann. Is there an Albanese for these kind of forms? So first strategy, construct an Albanese at least for a fixed cover. So it looks like kind of natural to do. So the setting is, you remember, so now I have no D. I take any cover, ramified, what you want. And now I look at just at this as this sheaf. which certainly lies here. And now you look at this. And the question of existence of an Albanese is there an abelian varieties which parameterize these forms, like the usual Albanese? You see? And it turns out to be a very subtle question, even for curves. So the natural thing to do is, like I did before, is like quotient the Albanese upstairs so that you keep only the forms you are interested in. So you look at the orthogonal in the dual here. So you are upstairs, and here you have the quotient, which define the Albanese. And you look at something a bit wild, is the image of this. So people in foliation can think of this, in fact, as giving you a foliation on the Albanese, right? And you want to do some quotient with the Zariski closure of this. Of course, it can be very wild. So it should be really special that you end up with a nice space when you quotient by a foliation. So what you do is you take the smallest abelian subvariety, which contains this guy, right? And now you take the quotient. And this is your definition. So there is no D, so just a gamma, and by definition, it's just this. Right? So this guy has, by definition, the good property that if you take one forms on this quotient, you pull back, it will end here. The question is, as for the usual Albanese, do you recover all forms? So this puzzled us for a while before we understand that the question in general is no. In general, not enough to recover all V. So you can cook up some examples, in fact, already on curves. So this is related to the theory of prime varieties. So if you take covers of curves, you look at the Jacobian, and essentially the prime variety is the kernel of the induced map between Jacobians. And you see that if you take such a construction, you could certainly achieve examples, very easy, such that this dimension grows as you want. So this is good. You have more forms upstairs, which lives in this pullback. But when you do this construction, in the end, you end up essentially on the Jacobian of C. You never leave the Jacobian of C in the case that the prime variety is simple. Because this means essentially that if the prime variety is simple, you have to take all the prime variety, and when you quotient, you end up here. And this is super bad, because our supposed new Albanese cannot detect these forms. So we cannot use any Albanese here, like this at least. Maybe there is a more clever way to do this, to do the classical statement. So there is but still it could happen that it works. And then there is some work, but you couldn't prove some more. So this was a first result that we did with Quebecus, is that indeed, if if there exists a gamma, and you are lucky enough that you end up with a Albanese of big dimension, then you can work. Then Bloch-Ochiai is okay. Meaning you can prove both statements. So X will not be special and there is no dense intercurve. But, okay, this is not satisfactory completely because of what I just told you. You cannot work with this in general. So we had to be a bit more clever and somehow give a proof without using Albanese. So this is the theorem indeed that so I formulate just the, so we can formulate everything for pairs, but here let's forget about this. Then X is not special. So, okay, so I just have 5 minutes. So rather than giving you general ideas, maybe I can explain you ideas of proof in the simple case already of a surface. Okay, ideas for dimension 2. So maybe also, so I should say that here you see, so you have this setting. So this tells you that you have found a cover, not et al. Probably, where you have a lot of forms here. And this, in some sense, you are trying to generalize a statement of Campana, in some sense, which, and you realize what it is not easy. Because Campana has proof, somehow it looks like easy, but it's not at all easy. If you have et al., then X is special if and only if X is special. So invariance of the special property by et al. Cover, it's not easy. Why is it not easy? So the direction, suppose this one is not special. You have a Bogomolov sheaf. The question is, how do you descend it? So suppose your cover is Galois. So a priori, you have a Bogomolov sheaf upstairs. It has absolutely no reason to be invariant by the Galois group. And to prove this, you need all the theory of Campana of core map, in fact, to prove this. So this, you see, this is not easy. So certainly, when you take more general covers, it has no reason to be more easy, right? So you are trying to prove that here you have kind of positivity with this sheaf. Because, of course, in the et al. Case, this one is just the sheaf, the omega 1 upstairs, right? So, okay, idea of proof. So I'm in dimension 2, and I suppose that I have 3 forms, which lives here. Right, so there is you do a dichotomy. So the idea is that you will try to use the classical Castelnuovo de Francis theorem. So the first statement is, suppose you are not in Castelnuovo. So when you look at all forms, so you look at the vector space generated by these forms, and you suppose that there is no forms inside, such that you have 0 wedge product. Then what you want to prove is that when you look at the map, which will be defined just by looking at by these sections of the, here is the canonical bundle, second power, then in fact you prove that it's a meromorphic immersion under this hypothesis. So this is not a trivial statement. You have to prove this. This is the first thing you want to prove, is that this will imply immediately that in fact this sheaf is big. And if this sheaf is big, gamma is finite, k of x will be big. And you are finished. X is certainly not special, right? This is the goal. And in the other case, let's take 1 minute. In the other case, it means you are in Castelnuovo de Franquis. You can find two forms. So, there exist equal to 0. Then you do Castelnuovo, and you certainly have a fibration onto a curve, and your form descends. And now it's easy to construct a Bogomolov sheaf, so you can pull back some Bogomolov sheaf from C1 into X hat. So this will leave just being some pullback. Okay, and now you are kind of happy. You say, well, I've produced a Bogomolov sheaf upstairs. But you end up exactly with the same difficulty as I've explained you here. This sheaf has absolutely no reason to be invariant by the group of the covering. So you have to find another way to produce it. And so what you do, the idea is you consider the orbit of all these Bogomolov sheaves, and you look at the intersection of all the fibration. Okay, so you have the orbit under G, and you have all this map. Right? And you look at the product map. And what you prove, this is also non-trivial, is that this map will have an image which is of general type, and you can pull back the sheaf. So you see that you may have to leave this one here in the end. So the idea is, it's not totally correct, but the idea is that now you will pull back the canonical bundle of the image of the intersection of all fibration under the action of the group. And this will produce and since everything is constructed with your initial forms, it lives in the good sheaves. But now, it has the good property that it is invariant, and so you can descend it. Right. So this is what you have to achieve in general, all these two steps. Okay, so I think my time is over.